In this video, we will discuss the possibilities of intersection between a line and a plane. And here they are. There are three possibilities. In one case, the line and the plane are parallel, so there's no intersection between them. They're parallel, right? In another case, the line runs through the plane and it will hit it at one point only. And in the third case, the line is lying in the plane, in which case there is an infinite number of points of intersection because every point on the line is also a point in the plane. Now the procedure for checking these possibilities is to look at the equation, the vector equation for the line. It will have three components, an x, y, z, or I, j, k terms. Take those terms, they will have a t in them, substitute them into the equation for the plane, and try to solve for the parameter t. So this is a case in which the plane and the line are parallel. There's another way to tell that the line and the plane are parallel, right? If we had a vector in the plane, which we can find from this equation, and we knew the normal to the plane, which we can find from the equation for the plane, those two should be at right angles, meaning that the dot product between them would be 0. But the procedure we're going to use here, we're going to do this because that's how you will, that's what you'll do for the other cases. So here's, in this procedure, we start with the equation for the line. So this is the line, and we know what it is because we have its vector equation. Now we have an x component, a y component, and a z component, and I listed all those right here. And now we have an equation for the plane. So here's the equation for the plane. And we just substitute for the x. X is going to go here, the y is going to go here, t and all, and whoops, sorry, and the z is going to go here, and that gives us the equation right down here. So then we have one equation and the unknown t, which is a parameter that we have for the equation for the line, and we try to solve for t. In this case, we end up with 4 equal to 6, which is not true. So there is no solution. Because there's no solution, that means there's no intersection between the line and the plane. Now let's look at the case in which the line is lying inside the plane. So we're doing exactly the same thing again. We take the x, the y, and the z components for r, and we substitute them into the equation for the plane. In this case, the t's go away again, but we end up with 6 equals 6, which is true. That means that t can have any value. Whatever value t has, we will still get 6 equals 6. In this case, the line is lying in the plane because for every value of t, we have an equality here. Meaning for every value of t, there's a point along the line, and that point is also in the plane. And now the next one, of course, is the case in which the line runs through the plane and intersects at one point. And we've done exactly the same thing. Here's the components for x, y, and z from the line substituted into the equation for the plane. And the solution in this case is t equal minus 1/2. So in that case, there's a value for t, meaning at some t, at some value of the parameter, the line and the plane, that the line, the point on the line is also in the plane. So what is that point? Go back here to your equation for the line, substitute this value of t, and the values of x, y, and z that you get are the values for the point. That's where the line is going through the plane. So there's your value of x, y, and z. 1 minus -1/2 is 3/2, and etc. So those are the three cases. Let's look at them again. So we have the case of no intersection. In this case, that procedure we went through had no solution. In the case that the line is contained in the plane, there's a solution, and the solution is valid for any value of t, the parameter t. And for the case where the line intersects the plane, and of course we'll do it at one point, then we have a solution for t. And from that solution for t, we find the x, y, z coordinates for the point.